It's a pleasure to me present Juliana Fernandes Pimentel, a young Brazilian mathematician. She works in the Universidade Federal do Rio de Janeiro, UFRJ. Today we'll talk about blow up and grow up for parabolic PDEs. One more time, thank you very much for accepting give a talk in our virtual meeting, Juliana.
Okay, so thank you very much. Let me first thank both the organizers, João Vitor and Leandro, for this kind invitation, and congratulate both of you for this very nice initiative. And I should also say that it was a good surprise for me that you found this, let's say, good gender balance of speakers in this meeting. Was a very good surprise for me, and I was really happy about that. Okay, so let me start. So this is the title of my talk. I hope you can see my pointer and my slides here. So we're going to talk about blow up and grow up for parabolic PDEs. Let me just say that by blow up, I mean blow up in finite time, and by grow up, I mean blow up in infinite time. Okay, so basically we're talking about unbounded solutions, unbounded with time solutions for the parabolic PDEs. So that's more or less the outline of my talk. So we start with some introduction, some preliminaries. So this is the class of equations that we are going to address. We define what we mean by heteroclinic connections between the solutions. And then after that, my talk is going to be divided into two parts. The first part about the grow up solutions, and then the blow up phenomena. So it's basically these two parts. Okay, so let me start. So we are going to talk about this class of equations. So it's a reaction diffusion equation here, defined always in a bounded domain. So it's always a bounded domain in Rn. And here you can choose Neumann or Dirichlet boundary conditions as you prefer. And we always are going to assume some smoothness for this function f. And our goal here would be to consider the case where your function f, your nonlinearity, is non-dissipative. It's non-dissipative in the sense that you do have unbounded solutions for your problem, okay? And since my background is in dynamical systems, so I can't avoid myself to think about the asymptotic behavior of solutions. So, which is in this setting is equivalent to study the stationary solutions of your problem, the solutions of the elliptic problem, as well as the heteroclinic connections between those. And in the specific case of unbounded solutions, which are the blow-up profiles that can be reached by your unbounded solutions. Because these structures together, they form what it's called an attractor for your equation. And that means that after some, let's say, very long time, that's what you see. So every solution, it's approaching this structure of stationary solutions and the heteroclinic connections between stationary solutions. So this is precisely what we are going to be interested here. Which are the asymptotic profiles, the blow-up profiles, the grow-up profiles that appear, and what are the heteroclinic connections that appear between those structures, those equilibria. So what do I mean by heteroclinic connection? So this would be a classical notion of heteroclinic connection between two stationary solutions, okay? So this is the classical notion. So you take any two stationary solutions of your problem, V minus and V plus. So these are solutions of your elliptic problem. And by heteroclinic connection between those, I mean an entire solution. An entire solution is a solution that is defined for every real time. So since minus infinity until plus infinity. And this entire solution satisfies this. So when you take the limit backwards in time, you reach one of those stationary solutions. And then when you take the limit forwards in time, you reach a different, the other stationary solution V plus. So this would be the trajectory of your function. So this is what I mean by a heteroclinic connection between these two stationary solutions. So, but here U is a bounded solution. So this is a classical solution, a bounded solution defined for every real time. So one main difficulty that we find here when we are talking about blow up or grow up is that, let's say if your solution U is unbounded, then this point here, for example, this stationary solution should be at infinity. So that's a bit more complicated to analyze, because you're going to reach this point with infinite time, but your solution is becoming unbounded. So this point should be at infinity. The other difficulty is when you're talking about blow up is that your solution exists only until a certain time, capital T. So what do you do after that? How can you reach this solution if you don't have existence anymore? So one possibility would be to try to reach this stationary solution by some continuation after the blow up. So that would be a possibility. Okay. So let me start then with the, let's say, the most treatable case, which is the case where you have bounded solutions, only bounded solutions. So I'm talking about the dissipative version of the problem. And by dissipative, I mean that all the solutions, they are defined globally in time. So you have solutions defined for every positive time, no blow up at all. But in addition to that, you have asymptotically uniformly bounded solutions as time goes to infinity. So every solution is going to be eventually bounded. So that is, let's say, the best case scenario that you can find. And here, if you're talking about the bounded, only about bounded solutions, then if you want to find that structure that I mentioned, the stationary solutions and the heteroclinic connections between those, this is exactly the set of all entire solutions, of all solutions that are defined for every real time. So they exist negatively in time and positively in time for every time. And this is what we call an attractor. This union of all these entire solutions is what we call an attractor. So this is what we are interested in. And let me say that in one-dimension space, this is much more treatable because we have, additionally to the tools that we usually have in this dissipative setting for parabolic equations, in 1D we have an additional one, which is, let's say, somehow it's a discrete Lyapunov functional that you only have in 1D. So that allows you to find exactly the heteroclinic connections that you can that exist between stationary solutions. So you have a much more complete picture of what is going on after a very, very long time in your problem. And this has been done by many, many people: Brunovsky, Fiedler, Chaffee-Infante. They studied the whole structure of heteroclinic connections for the so-called Chaffee-Infante equation. Carlos Rocha, Giorgio Fusco, Dan Henry, Joe Smoller, Matthias Wolff, a lot of people that have been working on heteroclinic connections in the 1D parabolic equations. In the higher dimension, this can be a bit more complicated, and we have some partial results. And yeah, this is just a few references here. Okay, so let me start with the previous development. So what people have done for the dissipative setting. So now I'm only talking about bounded solutions. So this is the only kind of heteroclinics that we are considering now. So only the classical ones, the ones that are connected by bounded solutions. So here I even added a spatial variable here in an advection term, but I am working in 1D. Okay, so this is what they have done for this case. Here's Neumann boundary conditions, some regularity for your function f. But since you want to ensure that you have a global existence for every solution, and in addition to that, you want that every solution becomes eventually bounded. So you need some further somehow strong conditions on your function f. So let's say you have this sign condition and this growth condition. This is not necessary, but it's a sufficient condition so that you are in this setting. So you don't have, you have no blow up and everybody's becoming eventually bounded. So you can study this parabolic problem in the space of functions x. And this is what they proved. So what you see after a very long time, what you see is exactly the structure that I mentioned to you. What you see is the stationary solutions of your problem, the solutions of the elliptic equation, and the heteroclinic connections between those. So this is a notation. So this is the set of all the heteroclinic connections connecting the stationary solutions V and W. Okay, so this is what you see. But actually this holds in any dimension. This part of this result you have for any dimension. but what you get in addition in 1D is this one. So you know exactly when two given equilibrium points they are connected. So given any two stationary solutions U and V, you know when they are connected, when they satisfy this condition over here. Okay, I'm gonna tell you what it is in a minute. So this means that there exists a connection between U and V if and only if they are adjacent, if they satisfy this condition. And of course, you have these connections, they go from higher to lower Morse index. Okay, this criteria for connection, so let me just tell you that this part of the result only holds in 1D, okay? So this condition is very simple to check because here we are in 1D, so our stationary solutions are functions from R to R, actually here from 0 pi, from the interval 0 pi to R, so it's very simple to check this condition. Before I tell you what it is, let me just tell you that we use this notation. So Z of U is exactly the number of zeros of U. So any continuous function, here U is going to be an equilibrium for us. So any continuous function, so it's defined on 0 pi, taking values on R. Z of U, it's the number of strict sign changes of U. So the number of times you change the sign of U. So this is the condition to be connected. So you take any stationary solutions, U and V, and since Z is the number of zeros, so this is the number of intersections. So since V and U are functions from R to R, you can count the number of times that they intersect each other. The graphs intersect each other. So this is this number J. So if U and V to be connected, they are connected if and only if there is no other equilibrium W blocking this connection. So you have two stationary solutions, and they are connected if and only if there's no other stationary solution W that is blocking this connection. And how W can block this connection? If and only if W satisfies these two conditions. So the number of intersections between V and W, W and U, and V and U are the same. They're all given by the same number. And W of 0 is between U of 0 and V of 0. So if W satisfies this condition, then W is blocking the connection. So it's a simple condition to be verified. So you know exactly when two stationary solutions are connected. So this result, this part of the result, the second part of the result was proven by Bernard Fiedler and Carlos Rocha in 1996. And this notion of the adjacency was actually proved a bit later by Matthias Wolfru in 2002. Okay, so what are the main tools that they have used? Of course, the gradient structure of the problem, and this is not a 1D, only 1D feature. Of course, you have it for higher dimensions, but the more specific tool that they have used here that I mentioned before, this discrete Lyapunov functional, is this one, is exactly the zero number that I just defined. So if you look at the zero number of the solution, along the time, this is going to be a non-increasing function. So this is saying to you that if you start with an initial data with a certain number of oscillation, as time goes to infinity, this number of oscillation can only decrease with time. Okay, so this is the condition, but this only holds in one dimension. So this was proved by Matano in 1982, and then Angenent in the final version by Angenent in 1988. And this is another tool. I'm not getting to the details, just to mention that if you want to prove that this criteria is necessary and sufficient, at some point you're going to have to construct the heteroclinic between two equilibria. You want to prove that there in fact exists a heteroclinic connection connecting those two stationary solutions. And in order to do that, they have used this, this map introduced by Bernard Fiedler and Pavel Brunovsky in 1988. It's called the Y-map, and the Y-map basically gives you all the nodal properties of the solutions that are in the unstable manifold of some equilibrium. So they prove that this map is actually surjective. So you can given any set of nodal properties, you can construct, you can prove that there is a solution with exactly these nodal properties that you prescribed before. So this is how you can construct a heteroclinic connection between two equilibria. So these are the tools. The first one, it holds in any dimension, but the other two only one dimension. Okay, so this is what we have for the classical notion of connection. When you have only bounded solutions, you can use these tools and you can get this result. But now let us talk about the case where you have blow up, where you have unbounded solutions. And we start with the grow up. So now we start the first part of the talk. So the first part of the talk, we're going to talk about grow up solutions. So solutions blowing up only in infinite time. So we don't have blow up here. So we start with this problem. So our nonlinearity is of this form. B is a real number that it has to be greater than the first eigenvalue, which in this case is 0. And G is a function that it has to grow less than linear. So this is just to ensure that you have a linear growth at infinity at least. So you have an asymptotically linear growth. And the function G is Lipschitz. So this would ensure global existence in time for solutions, so no blow up. But this linear growth will ensure the existence of unbounded solutions. So you do have at least one solution blowing up in infinite time. Okay, so we are going to talk about the heteroclinic connections between the solutions, but the problem here is that since you have these unbounded ones, you cannot only treat the heteroclinic connections between bounded solutions and these stationary solutions, because you have something that is escaping to infinity. And you need to check what is going on over there, what is going on to this solutions escaping to infinity. So actually you can, that's the same as restrict yourself to the solutions that are bounded, but only in the past. So these are the connections that we're going to be interested in now. They're not bounded forwards in time, but they're going to be bounded backwards in time. So this was already treated in some other contexts and by some other people here. And but they're not exactly treating the heteroclinic connections. They are mostly interested in the description of the attractor for the problem. And here you have some characterization of this heteroclinic. So this is a more recent work by Nitsa Bengal, where she discussed about this heteroclinic connections in 1D. So this is what we did. So now we are talking about 1D reaction diffusion equations with the grow up. Okay. So we have an equation like that in one dimension. And here I chose G to be bounded, but it was sufficient to take G not growing as faster as linear, smaller than linear. And B is greater than the function, the first eigenvalue. So it's a positive real number. So this is what we get in this result jointly with Carlos Rocha in 2016. We managed to get these heteroclinic connections in this setting. So we took care of what is going on in the bounded portion, so the stationary solutions and the heteroclinic connections, but we didn't lose track of the solutions that were going to infinity. So we also saw what was going on there. And what you have is more or less something like this. So let me just tell you that in this talk, every time you see a dot, so every time you see a dot is a stationary solution, and every time you see an arrow like this, a line with an arrow, is a heteroclinic connection, okay? So this is more or less the picture that you have in this case. So this part here, V1, V2, and V3 and V5, these are the stationary solutions of your elliptic problem. So you have an equation like that. These are the stationary solutions, and these are the heteroclinic connections between them. And this is easy to do because you can use the dissipative techniques. You can use the techniques that they have used before. So the problem is what happens with those that are escaping to infinity. So we proved that this grow-up solutions, they're going to infinity. They are going to infinity exactly in the directions of the eigenfunctions of the Laplacian. So this is not a coincidence. We chose this notation minus phi 0, minus phi 1, to exactly denote the direction of the eigenfunctions, let's say plus and minus phi 0, plus and minus phi 1, the first eigenfunctions of the problem. And the directions that you can escape are only the first directions, the eigen directions. Okay, it depends on the value of B. The larger B is, the larger are going to be the directions that you can escape to infinity. So you have a structure like that. So this arrow here, this represents a grow up solution escaping to infinity in this direction, okay? So we could construct everything here. Even at infinity, we could, I'm gonna tell in a minute how we did that, but even at infinity, we could find these heteroclinic connections between these structures. So we somehow, this is an extended phase space, let's say. So we were working in H01, in H1, but we include somehow, I'm gonna show in a minute, but we could include the infinity in this phase space. So you have something like this. So you have a similar result as before. You have only stationary solutions, you have only equilibria and heteroclinic connections. But the point is that now you have something that, so you have the stationary solutions, the bounded ones, but you have something at infinity. You have this points that you found at infinity and the heteroclinic connections between those. So, and we could also prove something that similar to the dissipative setting, to the classical notion of connections. We could also prove that two points here, they are connected if and only if they are adjacent, using that same criteria as before, okay? So we can, even considering unbounded trajectories here, even in that setting, we could find a condition to have an heteroclinic connection between solutions. So let me just recall you what it is, this criteria. So it's something like this: given any 2 points, you say that they are adjacent or they are connected, if and only if there is no other equilibrium W that is blocking this connection. So this is how W can block the connection. So I'm repeating this because if you notice here, I'm including these points at infinity. There are not exactly stationary solutions of your problem. So these are different objects. So how you can define the zero number of something that is at infinity? So when we use this criteria, actually we have to extend it to include these points at infinity, to include the unbounded solutions. So, but how we did that? We just noticed that, so these points at infinity, they are in the direction of the eigenfunctions. So you can extend this notion of this zero number, or the number of intersection, by, you can extend this naturally by using this idea. So you can identify this point at infinity with the eigenfunction, and then this can be extended naturally. Okay, so we have a similar result as that one. Okay, so let me just tell you how we construct that part at infinity, how we could find those, even those heteroclinic connections at infinity. What we did was to compactify our phase space. So you have something that is escaping into infinity, you have unbounded solutions, but what we want to do is to somehow make infinite finite, so that you can apply your techniques that you have for bounded solutions. So you want, what we did was to compactify the flow. Compactify the flow is basically project. What we did was basically to project our space. So you take your function space, your H01, let's say, or here we're going to take L2, but you take your space and you project into a bounded Hilbert manifold. And of course, if this is in infinite dimension, this is bounded, but it's not going to be compact. So that's why I'm using quotation marks here. It's not exactly compactification. What you're doing is making your function space into a bounded one. Okay. This is what you see in Poincaré and Van-Dixon projections. And there's a lot. This is actually not new. I'm going to give you a picture in a minute, but this is actually not new. You have some people that have already done that in finite dimension spaces. And here I just included this reference because Juliette Hell in 2013, she gave a formulation for arbitrary Hilbert space. So even in infinite dimension, she gave the formulation for this projection. So this is how it works. So how we can do that? So we take our space, our function space, and identify it with this one. So X Cartesian 1. So you are in X Cartesian R. So you have add have added a real axis here. And you take this space, X Cartesian R, and you find this upper hemisphere of radius 1. So Z is only greater than 0, it's just the upper hemisphere. And this has an equator, which is the point, which are the points where Z is 0. So you have a picture like this. So this is your phase space. This is where your dynamics is happening. So for each point there, you identify with a point here in this upper hemisphere. So why you're doing that? Because as you go to infinity, here you're going to the equator. So what was becoming unbounded there, now it's bounded the whole time. So here you don't have a grow up. So the solutions here are bounded the whole time. So this is why you do this, it's like a change of variables. So your equation was in new, and here you find an equation in the new variables, and then you study the equation here, okay? So as you go to infinity, here you're going to the equator. So you can find explicitly who are these key and z, these variables, and then you can find the equation in the new variables. So this n is your operator, your equation here, and this is the homotg. So this is just a notation, and I chose to write it like this just to tell you that actually this can be done even in more general, for more general equations. In principle, you can do this for every equation. But in our case, specifically in our nonlinearity that is asymptotically linear at infinity, we could simplify this equation a lot, because if you want to study the heteroclinic connections at infinity, what you want to do is to take z to 0, because as z goes to 0, so as z is going to 0, you are approaching the equator, so you are going to infinity. So z equals to 0 corresponds to infinity. So when you do this here, when you take this system and you take z to go to 0, then you have, in our case, you have a very, very simple equation, and you can find the equilibria there. So you find this discrete set of equilibria, which are given exactly like this. So you have stationary points at infinity. So these points, they coincide with those that I just mentioned before, that they are in the direction of the eigenfunction. So they are precisely those. Okay, so you have equilibrias like that. And you can even find which are the connections between those points by using this projection. You find something like this. So this part here, this is the bounded part. Okay, so this is just one dot, but it's going to be the whole bounded portion of this. So you have stationary solutions, you have solutions of the elliptic problem and heteroclinic connections between those. You have this here in the bounded part, but you have something that is escaping to infinity, and this is an indication on how this is for this particular problem. So you have this, what is called the Schoffen-Infante-like structure, because this is exactly what appears in the Schoffen-Infante equation. So this is what you have at infinity. So these points and the heteroclinic connections between them. So these heteroclinic connections at infinity, what do I mean by a connection at infinity? I'm saying that if you consider your parabolic problem, you have solutions that are becoming unbounded. So what I'm saying here is that when you take the set of all the solutions of your parabolic problem, you are approaching this structure at infinity. Okay, so if you add infinity, what you see is exactly this this picture here. So you are approaching this set of connections at infinity. So yeah, with this you have the whole constructor in the grow up situation. Okay, so this is how we did to get the heteroclinic connections in the grow up setting. So how we could generalize the idea of connections to include unbounded solutions. So the problem now is, so this is grow up. So this is in some sense easier because your solutions, they exist for every positive time. So it's easier to treat. But what about the blow up? Because your solution finished to exist at some time, capital tau, let's say, capital T, let's say, and how you can still reach some stationary solution after that. So now we enter the second part of the talk. This is, so the first thing you wanna ask yourself is, okay, so if you wanna consider blow-up connections, the first thing that you need to ask yourself is whether or not your blow-up are complete or incomplete, if they are complete or incomplete. By complete is complete blow-up is a blow-up that cannot be continued. So you cannot continue after the blow-up time. Incomplete is when you can continue after somehow. You can use some kind of continuation after the blow-up time. So you can continue your solution. So if you can do that, if you are in an incomplete situation, which is the case, for instance, of this function f here, of this nonlinearity. So this has an incomplete blow-up, the parabolic problem with this nonlinearity. So this was treated, for instance, by these people, Fila, Polacic, and Matano. And what they did for this problem is the following. They considered some, so they extended the notion of connection in this case. So what they did was to introduce this what they call the L1 connection. So what is an L1 connection? You have a classical solution from minus infinity until capital T. And then after that, so at this time you have a blow up, and then after that you continue your solution with a weak solution from capital T until infinity. And this extended solution can reach another stationary solution V plus. So you can connect V minus to V plus with a classical solution until the blow up time of existence, and then you reach the stationary solution with a weak continuation. So this is what they call the L1 connection. But the problem is, well, what if, so here actually you have a lot of problems. So this is, I think that they even don't know how to do that yet. As far as I'm concerned, the problem is you can continue and reach a stationary solution, but they don't know yet if you consider a different type of continuation, if you can reach the same stationary solution. So this is a very complicated setting. But in the complete case, you don't even have a continuation of your problem. So how we can do that? We're going to treat exactly this case. How we can construct connections if you have a complete blow up, if you don't have a continuation, which is the case of this u to the power p equation. So if you have this problem in 1D, you have a complete, in 1D you have a complete blow up, so you don't have an extension of solutions like that. So what we did, so we tried to apply the same techniques that we did before, that is compactifying your flow. So you have something that was unbounded before, but then you do this change of variable, and then you become bounded again. So this is what we tried to do here in this case. And we apply the same techniques. This is jointly with Lapisi and Honda. And what we did was try to apply the same projection, but the problem, let me just, a lot of information here, but the only thing that it's important is this thing. So the problem that, the main problem that we found when we tried to apply the very same technique, the very same projection, was that in this case, the blow-up set contains only a finite number of points. In that case, you have infinite points that are going to infinity. So the grow up happens in that case by an infinite number of points. But here you have, this only happens to a finite number of points in your spatial space, and 0, 1 here. So what we did was the following. So we adapt that projection to this case in the following way. So before, in the grow up setting, we did a projection of L2 Cartesian R. And here what we did was to project L2 Cartesian L2. So instead of adding a real axis, what we did was to add a function space L2 here. So now your upper hemisphere of radius 1 is given of this like this in this form. So this positive. And what you do here is the same as before. You have your space here, and then you have the upper hemisphere, and you project the points, and then you have this change of variables. So you start with your solution U, but then you have your equations in the new variables T and Z. But the main difference is that now Z, before Z was a number, so Z was homogeneous. Now you have your scaling factor Z, now it depends on X. So it's a different form. So this is why, actually, this is why we call this projection a non-homogeneous Poincare projection, because your scaling factor is not homogeneous anymore. So, so here just notice that the only possibility for Z to be 0 is when this is infinity. So Z of X equals to 0, this corresponds to blow up points. So these are the blow up points. But this happens only in a finite number of points. So let me just tell you that before, when you are going to infinity, actually, when you see the projection, your Z was going to the equator. So your point was going to equator, so Z was going to 0. So before, in the grow up case, Z equals to 0, the identically 0 is the infinity. Here, Z is equal to 0 only in a finite number of points. So you're not Z identically 0. So you're not in the equator anymore as you go to infinity. Let me give you a picture of that. You have something like this. So what you do is your point now is in this sphere. Okay, this is L2 Cartesian L2. So now your points are in this sphere. And what I'm telling you is that your solution of your parabolic problem is walking around here on S. So S means when Z is never 0, so you have no blow up. And the boundary of S is exactly when you have at least one blow up point. So you are walking here, and when you achieve blow up, you are in a point right here. And if you have continuation, if your equation is can be continued, then this continuation would happen in this gray area over here. Okay. So, but now the point is that now you are in a bounded structure. So now you can study the heteroclinic connections, the stationary solutions. Now you can try to do as before. The only difference to the grow up situation was that this boundary of S was exactly equator, and now this is not the case anymore. Okay. So since I don't have too much time, let me just give you a picture of the result. So this is what we were trying to do was to construct the heteroclinics in this case. Of course, we're talking about blow up, so this is much more complicated. This is until now we could only get partial results on that. So what we could do was to construct the profiles at infinity. Okay, so we could see what's going on at infinity, but not to every solution of the problem. We had to restrict ourselves, at least until now, to the unstable manifold of the trivial solution. Okay, so now we are only talking about connections from 0 to infinity. Okay, the blow up solutions going as time goes backwards to minus infinity, it goes to 0. So you have something like this. So this is the structure that you see at infinity. So this is the trivial solution, and this is blow up profiles at infinity. Okay, so this is what you see at infinity. So what is written here is the maximum and the minimum of your blow up profile. Okay, so this means that you have a blow up at infinity and then a minimum at with value U2. Here you have a minimum with value, a blow up at minus infinity, and then you have a maximum with the value U2. And then you go around and you have all the possible asymptotic profiles here, all the blow up profiles that can appear in your equation. So this is what you see. So this is not heteroclinic connection. This is a continuum of equilibrium. The heteroclinic connections are those. They're going from 0 to infinity, and they appear exactly in this form. So this is how we could construct the heteroclinic connections in the blow-up setting. So let me just very quickly tell you what we did. We studied the bounded classical connections. Then we applied the homogeneous Poincare projection to construct the heteroclinic connections when you have blow-up in infinite time, and construct the stationary, the heteroclinic connections between the stationary solutions. Then we introduced the non-homogeneous projected and applied that to the blow-up case. So we could construct blow-up connections and see what were the profiles that appear at infinity. And yeah, that's it. Just to mention that if you are in a higher dimension, this is much, much more complicated. And just to tell you that this bubbling phenomena, they can appear in a higher dimension as a possible profile, blow-up profile for solutions of the parabolic equation. And that's it. Thank you very much.
Thank you very much, Juliana, for the nice talk. Some questions or comments to Juliana Fernandes? If not, I have a simple questions. Can you prove similar results for a diffusion reaction diffusion process driven by the P-Laplacian operator? Because you consider the Laplace operator, morally the Hitch operator. What happens in the P-Laplacian case?
So there is a result on the P-Laplacian, which is, I think it's Ricardo Parreira that wrote it. So the problem with the P-Laplacian is that if you consider this very same equation, when you take the P-Laplacian, what you have is that with the P-Laplacian, you don't have unbounded solutions anymore. So what was unbounded before becomes bounded. So what they did was, what Ricardo did was to take the P as a parameter. So when P goes to 2, you become unbounded. So the unbounded solutions, they appear when P is exactly equal to 2 in that particular case. So it's the P-Laplacian actually would simplify the analysis, I would say, for this exact problem, for this reaction diffusion problem.
Regarding the non-local counterpart, is there similar results for the non-local operator, like a fractional Laplacian, or not?
For non-local operators, the connections specifically, I don't know about that. I know there are some people that study the global attractors, so the whole structure. I think the people from in USP, they are doing that. They are approximating the problem of, by local ones, and then they try to construct the attractor in that case. But this is the only kind of results that I know for the non-local.
Nice. If not questions more, thank you very much, Juliana, again.
Thank you.